Good day, friends, and welcome to today's WASE online channel. I'm Philip, your instructor. But before we start our lesson for today, I need you to subscribe for our channel if you've not already done that. We need your subscription for the survival of this program. To do this, just go below this video and tap the subscribe button. Thank you so much for doing this for us. Now let's look at our activities for today. We are continuing with set and set operations. Today we'll be looking at the part 3 of this topic. And under this part, we'll be looking at properties of set operations. I believe we can start now. Now, we'll be looking at properties of set operations. And under properties of set operations, we'll be looking at three main properties. So first, we'll look at the commutative property. Then we'll look at the associative property. Then finally, we'll be looking at the distributive property. We will be looking at these properties in terms of these two operations: union of set operation, then intersection of set operations. So let's start with the commutative property. To better understand commutative property, let's look at the following example. If I give you 1 plus 2, the answer should be 3, right? Now, if I also give you 2 plus 1, the answer should be 3. Is that right? Yes, that is right. So, you realize that irrespective of how we flip the two numbers that were being added, we arrived at the same answer, 3. Now, because addition has this kind of character, we'd say that it has a commutative property. We are going to apply this same idea in sets. And what we want to find out is whether intersection and union have the same ability. So we are going to try the same on intersection and union, and we'll find out whether union has a commutative property or intersection also has a commutative property. Alright, so let's do this. So let's take the two sets A and B. The members of set A are 1, 2, and 3. And the members of set B are 2, 3, and 4. So first, let's find A intersection B. So A intersection B is 2, 3, all in curly brackets. I believe you remember how we arrived at this. We said to take the intersection of two sets, we look for the item that can be found in both sets at the same time. You realize that 2 and 3 appear in set A and in set B at the same time. So A intersection B will be 2 and 3 all in curly brackets. Now let's flip the two sets and turn it and make it B intersection A. So we have B intersection A. The members of B intersection A are also 2, 3, all in curly brackets. And this is right because if we are doing intersection, we still need to go into the two sets and get the items that are common to both sets, and we write them down in curly brackets. Here 2 and 3 are common to both sets, so write them down and put them in curly brackets. So it's right if we say B intersection A is 2, 3, all in curly brackets. So what do you think about A intersection B and B intersection A? It seems they are the same. And indeed, A intersection B is equals to B intersection A, because they all have the set 2, 3, all in curly brackets. So, like addition, we can say that intersection has a commutative property. Now let's look at the union of the two sets, then see whether we can get a similar result. So first we'll do A union B. So our A union B was 1, 2, 3, and 4. And I believe you know how we arrive at this 1, 2, 3, and 4 all in curly brackets. We said the union of two sets simply means you join the two sets together to form one unit without doing double counting. When we join them together, A and B, we have 1, 2, 3, and 4. Remember the 2 and 3 appeared twice, but we didn't do double counting. So that's how we arrived at A union B equals to 1, 2, 3, 4 all in curly brackets. Now let's flip the two sets and look for B union A. So this is our B union A. And in this case too, we got 1, 2, 3, and 4 all in curly brackets. So as usual, we just join the two sets together, B and A together, without doing double counting. And when we do this, we would arrive at that answer. So clearly, A union B is equals to B union A. Therefore, we would say that union also has a commutative property. Let's look at associative property. So first, we'll use the following example to explain the term associative property. Then afterwards, we would apply that concept on set operations. Let's look at this simple arithmetic. We have 1 plus 2 into bracket or plus 3. So when they give you something like this, you first add the items in the brackets. Then when you are done, you add whatever you got to the one outside the bracket. So first we would add 1 plus the 2, that will give us 3. And when we are done, we would add the 3 to the 3 outside the bracket, that will give us 6. Now let's look at this calculation too. And the difference between this calculation and the first one is that the bracket has moved to the other side. So here we have the bracket form around 2 plus 3, whilst in the first the bracket formed around 1 plus 2. But of course, we want to find out whether the change in position of the bracket had any influence on the results of this simple arithmetic. So first, we would have to add the items in the bracket. So we will add 2 plus the 3, that will give us 5. When we are done, we would add that result to the one outside the bracket. So 5 plus 1 will give us what? 6. So it looks like the change in position of the bracket did not have any influence on the results. Now, this property of addition is what we call associative property of addition. we want to find out whether intersection and union have the same property. Now let's apply the concept of associative property on intersection and union of sets. So we are going to use these three sets: set A, set B, and set C. Set A has the members 1, 2, and 3, all in curly bracket. Set B has the members 2, 3, and 4, and set C has the members 1, 2, 3, and 4. And guys, because of the limited space on the screen, what I'm going to do is this: I'll guide you so that you do this by yourself, so that you come up with your own results. So first we'll do set A intersection set B all in brackets, and that intersection set C, and that is going to give us 2, 3 all in brackets. So this is what you're going to do. You are going to use the three set A, B, and C to do this. So first, using the three set, find A intersection B. Whatever answer you get, find that answer intersection C, and when you do that, you get 2, 3 all in curly bracket as your final answer. And here we have A intersection into bracket B intersection C bracket close, and that would give us 2, 3 all in curly bracket. And in this case, this is what we're going to do. First, find B intersection C. Whatever answer you get, write it down. Then you find A intersection that answer. You get 2, 3 all in curly bracket as your final answer. So clearly, it looks like the position of the bracket didn't change our results. For each of the arrangements, we got 2, 3 in curly brackets, which means that A intersection B all in bracket intersection C is equals to A intersection all in bracket B intersection C bracket closed. Therefore, intersection has an associative property. So now let's find out whether union has an associative property as well. So now we have A union B all into bracket union C, and the answer is 1, 2, 3, 4 all in curly brackets. So this is what you are going to do. First, do A union B, and whatever answer you get, do union C of that answer. And when you do that, you should get the answer 1, 2, 3, 4 all in curly brackets. Next, we are going to do A union into bracket B union C bracket closed. And when we do this, you should also get 1, 2, 3, 4 all in curly brackets. It's now your turn. So you first do B union C. Whatever answer you get, write it down. Then you do A union of that answer. When you do it right, you get 1, 2, 3, 4 all in curly brackets. So clearly with union 2, it seems the result wasn't affected by the position of the bracket. So what this means is that into bracket A union B bracket close, union C is equals to A union into bracket B union C bracket closed. Therefore, union has an associative property. Now let's look at the distributive property. Let's use the following example to explain the concept of distributive property. Then afterwards we'll apply that concept on set operations. Let's use this simple mathematical problem. So we have 1 plus 2 all into bracket times 3. To do something like this, we will first need to solve the items in the bracket. The items in the bracket are 1 plus 2. So we solve for 1 plus 2, that will give us 3. Then afterwards we would multiply the 3 by the item outside the bracket, which is also 3. 3 by 3 will give us 9. However, there is another method for us to do this, and this method is called the distribution method. And indeed, that's where the distributive property is coming from. Let's do our distribution method in this box. To use distribution method to solve for this problem, all we need to do is to expand the expression 1 plus 2 into bracket times 3. How do we do this? To do this, we will first multiply the 3 by the 1 inside the bracket. And that will give us 1 times 3. We will then bring our addition. You then multiply the 3 by the 2 in the bracket. That will give us 2 times 3. We've now been able to expand the expression using distribution method. So let's solve for the final answer. So what we'll do is we'll multiply the 1 times 3, that will give us 3. Then we also multiply the 2 times the 3, that will give us 6. So the 3 in bracket will now be added to the 6 in bracket. So 3 plus 6 will give us what? 9. Now, because the two methods resulted in the same answer, we can say that multiplication is distributive over addition. In our next slide, we'll see whether intersection and union have this property. At this point, let's use this concept of distributive property that we have learned in set operations. We would work with the following sets: set A, set B, and set C. Now, let's look for the following operations: A intersection B all into bracket union C. Now, because of the limited space on the screen, I'm not going to do this for you, but however, I'm going to guide you so you do this by yourself. So first, solve for the item in the bracket. It is A intersection B. So use the above set to find A intersection B. Whatever answer you get, write it down. When you are done, do that answer union set C and write that down. When you do it properly, you should get this answer. That is 1, 2, 3, 4 all in curly brackets. Now let's use the distribution method to solve the same problem and see if we would arrive at the same answer. So first we'll need to expand the expression. When we expand the expression, we will get A union C all into bracket intersection B union C all into bracket. How did we get this? So first, the union C would interact with the A, then you put all of them into brackets, then you bring intersection. When you are done, the union C again would interact with the B, then you put all of them into brackets. So that's how we arrive at this distributive expression. So now this is what we are going to do. We will first take the expression in the first bracket, which is A union C, and we are going to use the set A, B and C to solve this. So A union C, solve for A union C and write your answer down. When you are done, go to the next bracket, which is B union C, solve for that expression and write it down. Now what you are going to do is this: do the intersection of those two expressions and write your answer down. If you do this properly, you would get this answer, that is 1 2 3 4 all in curly brackets. Clearly again, it looks like the two methods have resulted in the same answer. So what we can say is that A intersection B all into bracket union C is equals to A union C all into bracket intersection B union C all into bracket. We can therefore say that union is distributive over intersection. In our next slide, we shall find out whether intersection is also distributive over union. So let's look at that quickly. So let's find out whether intersection is distributive over union. And in this example, we'll be using the same sets A, B and C. First, we would look for A union B all into bracket intersection C. I believe you can do this. Anyway, let's do it together. So first, we will do the items in the bracket. So do A union B using the two sets, set A and set B. The answer we'll get, we'll write it down. When we are done, we will use that answer and do that answer intersection set C. That answer we will get, we will also write it down. If we do it properly, we will get this answer, that is A, B, C and D all in curly brackets. Now let's solve this using the distributive method. To use the distribution method, we first have to expand the expression A union B all into bracket intersection C. When we do this, we would get A intersection C all into bracket union B intersection C all into bracket. I believe you remember how we arrived at this expression. So what we did was we took the intersection C and we interacted it with the A, and when we did that, we got A intersection C. We then wrote the union, then we again came back, took the intersection C and interacted it with the set B, and we got B intersection C. So that's how come we arrive at this distributive expression. Now let's solve for this. So for you to do this, you first have to do the item in the first bracket, that is A intersection C. So to do this, we'll use the set A and the set B. We'll look for their intersection and we'll write it down. When we are done, we go to the second bracket, B intersection C. we would use the set B and the set C. We would find the intersection of these two sets and we'll write our answer down. When we are done, we will then find the union of those two answers and we'll write that answer down. If you do this properly, you would get A, B, C, D all in curly bracket. Again, the two methods resulted in the same answer. So what this means is that A union B all into bracket intersection C is equals to A intersection C all into bracket union B intersection C all into bracket. Therefore, intersection is also distributive over union. Well, friends, this brings us to the end of part 3 of set and set operations. We can move on to the part 4 of this topic, and in part 4 we'll be learning to describe and identify various regions of the Venn diagram. In this part we'll focus on two intersecting sets. Thanks very much for staying with us, and please subscribe for this channel if you have already not done that. We need your subscription for the continuation of this program. Also, once you subscribe and we make or come up with new videos, we will get you alerted. Thank you. Stay safe until we meet again in the next video.